Hello, welcome to another edition of Physics Conspire. I am your instructor, Mr. Andrews. Today we want to talk about three things, three laws to help us be able to predict how an object moves. Alright, so if you remember, before we try to answer the question, well, what causes an object to move? And we said that a force causes an object to move. It'd be really helpful now if we can be able to predict how an object might move, or to be able to predict the motion. These three laws were put forth by Sir Isaac Newton, a British physicist and mathematician in the 17th century. He expounded upon work done by Galileo. Newton's first law is known as the law of inertia, and it says that an object at rest or an object in motion with a constant velocity will stay at rest or in motion unless acted on by an outside force. Think of inertia as this. Think of inertia as your 2-year-old sister who just learned the word no. Let's say inertia is playing with her doll, and you tell inertia, it is time to go to bed and brush your teeth. What does inertia tell you? Inertia tells you no. Inertia just wants to keep on doing what she's doing, right? Or let's say we're at the park and inertia is running up and down the field, big field. It's time to leave. Inertia, it's time to leave, come on, let's go. What does inertia tell you? Inertia says no. Inertia just wants to keep on doing what she's doing. And so again, Newton's first law is an object at rest or an object moving with a constant velocity will stay at rest or move with a constant velocity unless acted on by an outside force. How do you get inertia to move? How do you get inertia to stop playing with her doll or to go back with you and to leave the field? You have to force her. There has to be some interaction with the outside environment. The most important condition to Newton's first law is an object being either at rest or moving with a constant velocity. In both cases, whether at rest or moving with a constant velocity, the acceleration of the object is zero. So if this is the case, if the acceleration of the object is zero, then we know that the net force on the object is also zero. Our object is in a state of equilibrium. So then we can pose another question. How do we really know if an object is at rest or moving with a constant velocity? It may seem relatively simple, but there is still something to this. We know that the acceleration is zero, and well, we know that our net force is zero, so we can't look at any of those. So let's use this illustration to help us understand. Let's say you're going on a trip on a train, and you pick a book out of your bag to read. To you, as you're reading, well, the book is at rest. It's not moving anywhere. Let's say now that there's someone at the train station waiting for the train to come. If they see you on the train and they see the book moving. Why? Well, it's based on their reference. It's based on where they are in relation to the book. You and the book are moving at the same rate. So to you now, the book is at rest. To someone else, in a different reference frame, the book is moving. So whether an object is at rest or moving with a constant velocity will depend upon our reference frame and where we are. Newton's first law just simply helps us predict the motion of an object when it's in equilibrium, when there's no net force, and when the acceleration is zero. Newton's second law helps us predict the motion of an object when there is a net force and when there is an acceleration. And when there is an acceleration, that means that our object is now either speeding up, slowing down, or changing directions. And it simply says that the acceleration of the object is proportional to the net force on the object and inversely proportional to its mass. This is just a relationship between the acceleration, the force, and the mass of the object, and we can determine any of these quantities through Newton's second law. From Newton's first law, we know that an object has to interact with its environment in order for it to accelerate. Newton's third law helps us predict the motion of an object when it does just that, interact with its environment. We've all heard, for every action, there's an equal and opposite reaction. Well, that's Newton's third law. And it's simply saying that if two objects are interacting, that the magnitude of the force on each object is the same. However, the directions of the force are opposite. So, for instance, if I had a hammer and a nail, and I were to hit the nail with the hammer, it's saying that the force of the hammer on the nail is the same as the force of the nail on the hammer. Take that! Take that! I'm not going to be bullied by you no more. The forces are the same, but the direction of the force, they're opposite. So the nail is pushing back on the hammer and the hammer is pushing on the nail. Opposite direction of forces, but the magnitudes are the same. The reason why the nail moves or accelerates differently than the hammer is due to their mass. The hammer is more massive, has more mass than the nail does. So therefore, their accelerations or their movements are different. That's why the nail is driven into the wood and the hammer not so much. Alright, let's talk about Newton's laws. And we're using Newton's laws to predict how an object might move. So, Newton's first law is the law of inertia, and it simply states that an object at rest or an object in motion with a constant velocity stays at rest or in motion unless acted on by an external force. So what does this mean? This means that the net force on the object is zero, the acceleration is zero, and then this is an equilibrium condition for our object. Okay, so, well, two criteria for Newton's first law is an object being at rest or moving with a constant velocity. Well, so then what's the difference between rest and a constant velocity? Well, we know this. We know that the net force is zero for both of them, and the acceleration is zero. All right? So then the difference comes in the reference frame. So if I'm on a train and I have either my cell phone or a book or some other device, the object is not moving in reference to me. In reference to me, it's at rest. So objects appear to be at rest if the reference frame coincides or moves along with in the same way with the object. However, if someone were at the train station and they were to look at the object, either the cell phone or the book, it would appear to be moving. So, objects appear to be in motion if the reference frame does not coincide or go along with the object. An object can be in motion without acceleration. It just means that it's moving with a constant velocity, and that just means that our reference frame is different from our object. Okay, Newton's second law, we know this, that the acceleration is equal to the force or net force on an object divided by its mass. Stated a little more succinctly, the acceleration of an object is proportional to the net force on the object and inversely proportional to its mass. This means that the net force is not zero. And if the net force is not zero, then we have an acceleration. And if we have an acceleration, then we do not have equilibrium. Newton's second law, there is no equilibrium. The object is not in equilibrium in Newton's second law. Just by chance, if the net force is zero, then we have Newton's first law here. So really, Newton's first law is just a special condition of Newton's second law. All right, final law. The action-reaction. If two objects interact, the magnitude of the force on both objects is equal. However, the forces are in opposite directions. So, we've all heard it stated a different way. For every action, there's an equal and opposite reaction. Well, what does this really mean? It means that forces act in pairs. So for instance, if I have a hammer and a nail, well, It means that the force on the hammer by the nail is equal to the force on the nail by the hammer, only in opposite directions though. So there's the difference. Let's talk about some everyday forces. Weight, for instance, is one of those forces. And weight is going to be a force that's due to the gravity or gravitational field on an object. And that gravitational field will vary by location. So we'll say that W equals weight, and that is equal to our mass times our acceleration due to gravity, which we'll call G. Weight always acts downward toward the center of the mass, or in our case, the center of the earth. And the mass of the object, of course, does not change. However, its weight can. So, if I was on Earth, the Moon, or Mars, an object's weight will be different in all of these locations, even though the object has not changed. Its mass will be the same, but its weight will be different. So if I wanted to lose weight without dieting or exercise, I can just get a one-way trip to the Moon or to Mars. Maybe you can go round trip, but you would pick up the weight again when you come back. It might just be easier to do diet and exercise. All right, let's see if we can determine the weight of a 15 kilogram backpack in these three locations. Remember, the weight is equal to the mass times the gravitational acceleration. Here we go. I have our gravitational accelerations here at the bottom. Earth, we know it's negative 9.8. On the Moon, negative 1.6. And on Mars, negative 3.7. The negative only means that it's headed toward the center, that in all intensive purposes, its direction is downward. So, on the Earth, we'll multiply 15 kilograms times negative 9.8, and we'll come out with our weight of 147 newtons. Same thing goes for the Moon, except we're using its acceleration due to gravity, at 24 newtons. And on Mars, just a little bit heavier at 56 newtons. So again, the mass of the object doesn't change, however the weight can, and that's going to be based on its location. Okay, let's talk about another everyday force that we have to have in order to carry out our daily activities. The normal force is a force that acts perpendicular to the surface on an object. By normal, we don't just mean regular or average. We mean perpendicular. So the normal force, again, is a force that acts perpendicular to the surface of an object. Perpendicular being 90 degrees. So here we have our weight. We know that our weight is pushing down on the object toward the center of the earth. And then the white line, the white horizontal line, represents the surface. So the normal force is pushing up on the object perpendicular to the surface. Now, because the object is in equilibrium, then we know that the net force is equal to 0. So this means that the net force in the y direction is equal to 0. Well, what composes the net force in the y direction? What is it made of? It's made of the weight and the normal force. Well, I know that the weight is acting downward and the normal force is upward. So we can solve for the weight and we can see that, or solve for the normal force and see that the normal force is equal to the weight. Our weight is equal to our mass times gravity, and that is our normal force. If the angle of the surface changes, so does the normal force. So let's change the angle of the surface. Our weight still is acting downward. However, the normal force now is going to be perpendicular to the surface. Well, we'll have to draw another triangle. So we'll just bring our weight down. We can move it down and draw our normal force here. And we see that the normal force is now a component of the weight. the normal force is the adjacent side of the triangle. And so we can solve for the normal force using the cosine of the angle, and we come up with our normal force is equal to our weight times the cosine of the angle. As the angle increases, the normal force decreases. So let's see. Let's try to determine the normal force on the following objects. I have a 10 kilogram object. Again, the white horizontal line represents the surface all the way to the left. So I know that my weight is equal to my mass times my gravitational acceleration. I'm here on Earth, so my gravitational acceleration is 9.8. So then the cosine of the angle, well, what's my angle here? My angle is 0 degrees. So I know that my normal force is equal to 98 times the cosine of 0 degrees, or 1, or my normal force is equal to 98 newtons. Here, my normal force is equal to 85 newtons. It's going to be 98 times the cosine of 30 degrees. And in the last case, my normal force is equal to 49 newtons, 98 times the cosine of 60 degrees. Okay, now let's talk about friction. Friction is a force that resists an object's motion. This force helps us to walk, it helps us to drive. We need it for our tires, for sports and cleats. It even helps us to operate on patients or animals and much more. Friction is caused by the force between atoms on a microscopic level. On a microscopic level, the surfaces of even really smooth objects are rough and jagged. And so there are cracks and crevices that the atoms fall into and bind together, and we have to break each and every one of those bonds when we try to move something. Our equation or relationship for friction is friction, the little f, is equal to mu times the normal force. Mu is called the coefficient of friction, and it's a value usually between 1 and 0 that determines how an object interacts with its environment. A value of 0 would mean that there is no friction. A value of 1 would mean that the friction is equal to the normal force. Okay, so we know that friction resists the motion of an object. So now let's see if we can determine the direction of friction for the objects below. All the way to the left. Remember that velocity determines the direction of the object. So if our velocity is to the right, then that means that the force of friction must be to the left. And on the object on the right, if the velocity is to the left, then the force of friction, well, must be to right. Now, there are two types of friction. There is static friction and kinetic friction. If you've ever tried to move any furniture inside your home, you've come in contact with both types of friction. Static friction is a force that keeps an object from moving, and kinetic friction is a force that resists the motion of an object. Now, these two may sound very similar to mass. However, mass is the property of an object, whereas friction results from the interaction between the objects and its environment. Static friction can vary up to a maximum value, and we'll call that F max. Now, if you've tried to move a really heavy object, say your sofa or couch at home, and you applied a force, it probably didn't move at first. You just encountered static friction. And even if you pushed on it a little harder, it still may not have moved. You had to continue to apply a force until finally it began to budge. As a force is applied, an object still may not move. As the force increases, static friction also increases until it reaches a maximum value. If the force increases past this value, the object begins to move and kinetic friction resists its motion. So once you've applied enough force to the sofa, it began to move. You still had to keep on applying the force, but now it was a little bit easier. Now kinetic friction was trying to resist the movement of the sofa. Kinetic friction will always be less than static friction. Okay, let's see if we can determine the maximum amount of friction for the following objects here. So I have my 10 kilogram object on a level surface. The coefficient of static friction is 0.7. First, we need to determine the normal force. Well, remember that the normal force is equal to my weight times the cosine of the angle. My angle is 0 degrees here. My weight was 98 newtons, so therefore my normal force is equal to 98 newtons. Now, I can apply this straight away to the equation for my maximum static friction. 0.7 is the coefficient of my static friction. 98 newtons is the normal force. I can multiply them together. So now, my object can resist a force of up to 69 newtons before it begins to move. After 69 newtons, my object will begin to move. Let's see if we can determine the force of kinetic friction for the following object. This is a little more complicated, but still we have all the steps and all the tools we need to figure this out. The first thing we want to do is draw a free body diagram with all of our forces on there. We know that there is the 50 newtons at 30 degrees. We know that our object has a weight. We know that it has a friction, a kinetic friction. At least we believe that it has one. And we know that it has a normal force. Now, even if we don't know the direction of our object that it may be moving in, we can assume a direction, and as long as we're consistent, all the values should work out correctly. The next thing we need to do is resolve the 50 newtons at 30 degrees into the x and y components. We've done that several times. We need to use the cosine and sine in order to do that. Now we want to draw a new free body diagram with the 50 newtons at 30 degrees resolved. Now we can determine the normal force. We know that the net force in the y direction is equal to 0. Well, we know that our object is not floating up in the air and it's not sinking into the ground. So in the y direction, our object is in equilibrium. Well, what composes the y direction? We have a weight that's going downward, so it receives a negative, and 25 newtons going upward, plus the normal force. So we can solve for the normal force. Now, the net force in the y direction, again, must be 0. If not, the object would be floating or sinking. Next, we can use our equation to determine the kinetic friction. We can plug everything straight away. We know that the value for the coefficient of kinetic friction is 0.5. The normal force is 73 newtons. So therefore, our force of friction is 36.5 newtons. So there are 36.5 newtons that are resisting our object from moving. There is a net force, though, of 6.5 newtons at 0 degrees, and the object's acceleration is 0.65 meters per second squared at 0 degrees. See if you can figure out how this is. I'll leave you with this challenge. Okay, there it is. Mission completed. Good luck.